All right, let's get started with lesson 4, chemical equilibrium calculations. Now in this lesson, we're going to show you how to use the icebox to solve a variety of different equilibrium problems. I guarantee you that if you learn how to use ice, you'll be able to organize your equilibrium problems, and it'll make it much easier to calculate the equilibrium problems that you're going to face. So our first problem that we have is a student is going to place 0.20 moles of PCl3 gas and 0.2 moles of chlorine gas into a 1 liter flask. And a reaction is going to happen, and it's going to produce PCl5. The equilibrium is going to be established, and at equilibrium it was found that the flask contained 0.12 moles of PCl3. And they want to calculate the value of the Kc, or the equilibrium expression. So the first thing we're going to do is actually determine the chemical reaction in the balanced equation. So we're going to take our PCl3, we're going to react it with chlorine gas. These are all gases. And it's reversible. We're going to form an equilibrium with PCl5, which is also a gas. The equation should be balanced. So now what we're going to do is draw an ice box for this problem. All right. So we have ice, Ce for ice. Okay, I is the initial concentration in moles per liter, and C is the change in concentration, and E will be the equilibrium concentrations that will occur here. Now, I would also, before I get started, I would draw or diagram out the equilibrium expression for this reaction, and I'm going to just put it over here. So Kc is equal to, remember, it's the concentration of the product first raised to the power, which is just going to be 1, over the reactants PCl3 also to the first power, and Cl2 to the first power due to the coefficients. Okay, now next I'm going to start filling in what I know from my ice table. So I do know that my starting concentrations, which are going to be 0.2 moles divided by 1 liter to get us in moles per liter, is just going to be essentially 0.20 molarity. And same thing with my Cl. My initial concentration of my product will be 0. Haven't made any. Now the changes. Now I do know that I'm going to lose reactant. How much, I don't know yet. So I'm going to minus x, and then I'm going to gain product, so that should be a plus x. And they're all 1-to-1 ratio because each coefficient is 1-to-1 in the balanced equation. So now at equilibrium, the question is, what is the equilibrium concentrations? Well, it would be 0.2 minus x, 0.02 minus x, and x. Okay? The question is, do we have any clue of what x might be? And the answer is yes. All right? What we know is that the equilibrium concentration for PCl3, so at equilibrium, PCl3 at the equilibrium is equal to 0.12 molar. Okay, because you're going to take your 0.12 moles of PCl3 and divide it by 1 liter, which is the volume of the container, and you get 0.12 molar. So that means really I can erase this term, fix my ice box here, and I know that really the equilibrium concentration for PCl3 is 0.12 molar. All right, so can I figure out my x factor knowing that? Absolutely. All right, because I can take my initial concentration, which is 0.20, minus my equilibrium concentration, and I should get my X value to be 0.08 molar. So X is going to be 0.08. So I can actually now substitute my X value as in each one of these situations. Erase that and put in 0.08, 0.08, and 0.08, okay? So I also know then that this X must be 0.08 because 0.08 plus 0 is, well, 0.08, right? And I also know that 0.2 minus 0.08 for this reactant is going to be then 0.12 molar. All right, so now I have used this icebox and my reasoning out what the equilibrium concentrations are. So now I can plug in all my equilibrium concentrations into my equilibrium expression and solve for Kc. So again, I'm going to take my product, which is 0.08 raised to the first power, divide that by 0.12 raised to the first power, and 0.12 raised to the first power. And I will then do the math, and I should get a Kc value. So Kc is equal to 5.56 if you do the math. So Kc is equal to 5.56. It is greater than 1. So Kc, being as large as it is, should tell us that this reaction is product favored. All right. So that's essentially the first problem, and using icebox to solve for the equilibrium constant. Okay, let's go to problem number 2. All right, so according to problem number 2, says the oxidation of NO to form NO2 occurs during the formation of smog. So when we start out with 0.06 moles of NO reacts with 0.06 moles of O2 in a 2, we got to remember it's going to be in a 2-liter container now, not a 1-liter. So we got to figure out our concentrations for a 2-liter container. At 500 degrees C, equilibrium mixture was found to contain a 0.20 moles of NO2, and they want you again calculate the equilibrium constant for this reaction. All right, so we're going to write out our chemical reaction here. So we should have 2 NOs. I'm just going to write it out, the balanced equation for this. Forms an equilibrium with 2 NO2s, and they're all gases as well. So they're all going to be found in the equilibrium expression. So I'm going to make an ice box here. Yeah, I should probably make this a little bit bigger here. Have a little bit more room to write. All right, so there's my ice box. ICE. All right, equilibrium expression for this is going to be Kc is equal to NO2, my product, over a reactants. I got to square that because of the coefficient of 2. NO, I'm going to square that as well. And O2 to the first. Okay, there's the equilibrium expression. Now, my initial concentrations, so I have 0.6 moles of each one, but it's in a 2-liter, so I got to take 0.6 divided by 2 to give me the actual concentrations, which is going to be 0.30 molar for each one of these. Right, and my initial, of course, for my product is 0. Now, change, we're going to minus 2x because of the coefficient of 2, minus x, and plus 2x for the product. All right? Again, the 2 because of the 2 in the coefficient. So the equilibrium concentration should be 0.30 minus 2x, 0.30 minus x, and 2x. All right? Now the question is, can we solve for x? Well, we do know that at equilibrium, the NO2 concentration at EQ, equilibrium, is 0.2 moles per 2 liters. So that tells us then that at equilibrium, the concentration of NO should be 0.10 moles if we divide those two. All right? So the question is, now we know that we can say that 2x, we can say 2x because we know that this right here, this concentration at equilibrium is 0.10 molar. So that means that 2x must equal 0.10 molar. So that means that x, if we divide 0.1 by 2, x would be 0.05 molar. Okay, so that gives us our x value. So now we're in business. So now I can essentially plug in my x value. This is minus 0.05. And this one here, oops, erase that, is going to be 2 times 0.05. So, and I already know what this is, so I'm going to actually erase that and put in 0.10 now, because I know 2x is 0.10. And I can also plug in x for these two values here. This is going to get kind of squishy here because that's a 2. So this is 0.05 and this is 0.05. Okay, so now I basically do my subtraction here to find the equilibrium concentrations, and then I plug those equilibrium concentrations into my equilibrium expression. So we can find Kc is equal to 0.1, which we got to square that, over 0.2, which is also going to be squared, times 0.25. And again, I get the 0.20 and the 0.25 by just doing the math here and here, the subtraction there. All right. So then when I do the math, I essentially will find this to be Kc is equal to 1. So Kc is equal to 1. All right. So that's essentially how we do that. All right, let's go to our next equilibrium problem. Now things are going to get a little different with this problem. All right, so we have our chemical reaction already written out for us. And this time we are given the Kc value. Right? The Kc value for this reaction is 6.78 at a specific temperature. All right? So the initial concentrations of NO and NO3 were both the same. And what they want us to do is to figure out what are the equilibrium concentrations, okay, given the Kc value now. So no different, we're going to still make an ice table. All right, that's what we're going to start out with. Since we already have a balanced chemical equation, we'll just do our ice table. Let me make it a little bit bigger this time. So we're going to make our ice table. All right. So this first will be for essentially each one. we go down, as you can see there, okay? For each box. All right. So again, we have ice. Okay. Equilibrium expression, Kc, is equal to NO2 over SO2 over NO times SO3. Right? There we go. Everything's to the first power because all the coefficients are 1. Okay, so now what we know is that our initial concentration is 0.03. I'm just going to go ahead and just do the first 3 there because to make it simple. All right, our products are going to all be 0. We don't have any product initially. So this is going to be minus x plus x plus x for our change, and therefore equilibrium, it should be 0.03 minus x and 0.03 minus x, x, and x. Okay? Now, we don't know what x is at all, but we need to still solve for x. And since we now know the Kc value, we only have one variable here, and that's x. So what we can do is plug all of this into the equilibrium expression. So it looks like this. So Kc, which is 6.78, is equal to x squared, because we're going to take our products over our reactants, so x squared, and we're going to put 0.03 minus x, but since we got another term of that, we can actually square that term as well, right? Because we can take this times this is going to give us 0.03 minus x squared, okay? So this is how the problem should look when we plug it into the equilibrium expression. Now we just need to solve for x, right? Hopefully you know how to do the math from here to solve for x. But in case you don't, let me do the algebra quickly. What I would do is try to get rid of the squares. So I would do the opposite. I'm going to take the square root of both sides of this expression. And that should get rid of the squares and make this much easier. When we do that, it's going to, let's see, rewrite this once we get the squares out of the way. Here we're going to get 2.604 equals x over 0.03 minus x. Okay, so now hopefully it will be much easier for you. So at this point then we can take 2.604 and multiply it by 0.03 minus x equals x. Okay, so now from here all you have to do is take the distributive property and collect like terms, and we should end up getting an x value of 0.0217. Okay, so make sure that you can do the math and solve for that and get the same x value that I do. So now we know what x is. We just need to plug in x into each one of our places in the equilibrium icebox. Okay? So in the end, what we should find is that if we plug in x and do the math, we should find that at equilibrium, NO2 is equal to 0.02. SO2 is equal to 0.02, and NO is equal to 0.01, and SO3 is equal to 0.01 as well. All right? So those are the equilibrium concentrations for this particular problem. All right? And that's essentially how you do it. All right, let's do the last one. Try to go a little bit faster here. Okay. Now, the K value here is something really important to look at because it's going to save you a lot of time. So the Kc value for this reaction that we're going to look at is extremely small. So that tells us that it should be very much reactant favored. We should have little product being made here. Most of it is going to be reactant because of the very, very super small Kc value. So the reaction here is we got water, and so water, H2O, in the gas form is going to decompose and form H2 gas plus O2 gas. Balance the equation like so. All right. So we get the initial concentration of the H2 gas, and they want to find what is the equilibrium concentration of H2. All right, so we're going to use an ice box just like we normally would. I'm going to set it up here right underneath. And we got our initial change in equilibrium concentrations for all three substances here. All right, so for water, we're going to start out with 0.10 molar. 0 and 0. Okay, the equilibrium expression for this, by the way, is Kc is equal to H2 squared in O2 over water, which is squared. And we can put water in the equilibrium expression because it is a gas in this case. All right, so we're going to use our ice table, minus 2x, right, because of the coefficient 2. We have 2x plus and x plus, okay? Now, at equilibrium then, it should be 1.0 minus 2x, 2x, and x. All right? So now we're going to plug this into our equilibrium expression. However, if we do that, we're going to get a very complicated problem that we're going to have to solve. So what we're going to use is known as the approximation method. And the reason why we can do the approximation method is because our Kc value is really small, which tells us that our value for our 2x, or our x value, should be extremely tiny. There shouldn't be much left. And so if we take our 0.10 minus whatever our 2x value would be, it would essentially be 0.10. We're not going to lose much of our original reactant. So what we're going to do is we're going to get rid of the 2x, this term right here, we're going to get rid of that in our equilibrium expression. And then we're going to do an approximation of what x is. And it turns out because of the x value being so small that we can go ahead and do this. All right, and I'll explain a little bit more of that in a minute. So we're going to go ahead and plug all these values into our equilibrium expression. So for hydrogen, it will be 2x squared. Oxygen would be x. And then again, for our water, we're only going to put in 0.10. And get rid of the 2x and approximate it that it's going to be so small that it's insignificant in this case. And that's going to equal to our 7.3 times 10 to the minus 18. All right? So if we do the math now, we should get something like 4x cubed over 0.10 equals 7.3 times 10 to the minus 18, which then should equal 0.10 times 7.3 times 10 to the minus 18 equals 4x cubed. So we divide both sides by 4, right? And what we're going to end up then with, if we do the math correctly, we should get, I'm going to bring it over here, so we should get 7.3 times 10 to the negative 19 equals, actually, nope, just kidding. Did the math wrong here. It should be 1.825 times 10 to the minus 19th equals x cubed. So then what we're going to do is take the cube root of both sides. Take the cube root, and hopefully you can do that on your calculator. If you don't know how to take the cube root on your calculator, look up the directions to do so. Alright, but we're going to take the cube root. Each calculator will be a little different, but it should give us an x value of 2.6 times 10 to the minus 5. Alright, so our x value we have now solved for. So we can plug in our x value into our equilibrium expression, and for hydrogen, which is what we're trying to find, we can take essentially now 2 times 2.6 times 10 to the minus 5, and this will equal our equilibrium concentration, which is going to be 5.3 times 10 to the minus 5. Alright? So again, if I take 2 times our x value, I will get the equilibrium concentration. So H2 gas at equilibrium has a concentration of 5.3 times 10 to the minus 5. Right? Now we could, if the problem asked for, we could solve for the equilibrium concentration for oxygen, which is our x value. So it would be 2.6 times 10 to the minus 5. That would be the equilibrium concentration for oxygen. And for water, all we would do is take 0.10 minus 2x, and that would give us the equilibrium concentration for water. All right? And that's all there is to it. All right? Now, I know that's easier said than done, but I would encourage you to look through these problems, go through this video again, and then work out the homework problems that I've given you, and see what you can do with them. All right? So that is it for now, and for the example problems that are in your study guides. All right? Till next time.